Well, in reality, we are not going to be solving vector problems by using rulers and protractors and graphically solving them. We're just not. To solve vector problems, we're going to use math. We're going to use trig and geometry to figure out what the resultant would be. And the process is not difficult, but can be tedious, meaning no one individual step of the problem-solving process is hard. But when you have lots and lots of little steps that you got to keep track of, then it becomes a little more difficult to keep everything together and keep your thoughts together. So one of the things I recommend before we even start any of these problems is write your work down, draw sketches. There are so many cases and times when I've seen students just get beat up by these problems because they refuse to write things down or draw sketches or show their work along the way. You're just really doing more damage that way than you are helping yourself. So trust me, I've been around a long time. Writing more down, showing the pictures, that makes it register in your head what's actually going on, so that you can answer what's being asked. So here we have the situation where I gave before with the box full of money, right? So I have the person A, B, and C. They're all pulling on the box of money with their respective forces, with their respective directions. Of course, this is an above view. North, south, east, and west. That's going to be our reference frame. And we already know what the answer is, well, at least roughly, because we had done it before with measurement, but let's do this mathematically. We want to know what's the result, which is A plus B plus C. And to do this, we're going to look at these forces, and instead of adding them graphically, we're going to look at these and assign the, we're going to, sorry, totally lost it. We are going to look at these vectors. We're going to gather up all what we call the x components and gather up all the y components of these vectors and add them together. Let me show you what I mean. So I'm going to add this out of order again. I'm going to do A plus C plus B. I had done that before. And if I were to sketch that off to the side, we get A, and I'm not using a ruler because I just want to show you the concept. And then C, and then B. And well, I hope we can all see that, you know, A and B are pretty easy to what we call resolve. Not to resolve, pretty easy to see how they're going to interact. In the previous example that I had done in the earlier work, I did A plus B plus C, where we saw that A was this way, and then B was this way. Now, if we stopped right here, A and B, we could find out what that intermediate kind of resultant is, right? We know A is pushing 250 this way, and we know B is pushing 100 this way. So if 250 one way, 100 another way, that would mean there's 150 difference. And that would be pointing in the way that the bulk of the force is pushing. We would know that if it was just a tug of war between A and B, A would win, and A would win by 150 newtons of force. So if vectors are along the same axis, you're literally just adding or subtracting the values depending upon direction. Just kind of like you did in the previous chapter with displacement. Right? You're along the same number line. When you have vectors at angles and in quadrants, then this method of just straight adding and subtracting doesn't work. Here I have A, I have B, I have C. A and B are in the x direction. I know it's north, south, east, and west, but really what we want to do is think of these vectors as x and y. We call that components. Well, A and B only have x components. A points in the positive x direction and B points in the negative x direction. So even though we're working with coordinate systems, we need to understand and assign positive values and negative values to each of those directions. Now C is in the, really if you drew C by itself, it would be in the third quadrant. And what we want to do is break up C into its what we call components. We want to break it up into a right triangle with an x leg and a y leg so that the vector itself is the hypotenuse to that right triangle. Now, when you break a vector into components, typically you want to do the x piece and the y piece, because well, that makes sense, right? Like if this is at an angle, I can pretend that this vector C is made up of two other vectors. So C is kind of is a resultant of its components. And what we do is we call this portion Cx because it's the x portion of C, and we call this Cy. This is the y portion of C. Now, note, direction is important here. We can't, and I can't tell you how many times a student does this. If they have a vector that points like this, and they're trying to break it up into components, a lot of the times I got a student just go this, and they'll make legs of a triangle, but there will be no arrows. That's wrong. Because if this is a vector C, we went from here to here. Well, if I'm going to do components, my components have to represent the fact that we're going from here to here. That means the direction of these arrows are important. The direction of the components are extremely important. So, now this drawing here, doesn't use the 30 degrees that was given to me. But a lot of the times, because of the way we're going to find the x and the y components, it pays to do the x-axis, then the y-axis, and then get that angle off of the x-axis. Well, that's 30. It's a coordinate system that's got to be complementary, so this is going to be a 60-degree angle here. Some students will know that this 30-degree angle corresponds with a 30-degree angle here because of alternate interior angles, which is fine. But let's stick with the angle here, 60 degrees. Now, if I know that's 60 degrees, I'm going to redraw this over here, and I'm going to kind of free up the that is not nice. I'm trying to draw C to make it look as uniform as I can in all these pictures. So this is C, and this is the x component of C. This is C, and these are vectors. This is the y component of C. This is C overall. Here's my 60 degrees. Now I can take this and use trigonometry to find the x and y portions, because I know SOHCAHTOA, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So I need to know that. So in this particular case, I know the hypotenuse. I know the hypotenuse is equal to 150. I know the angle is 60. So if I want to know C, I'm going to do that over here, or cx, the x component of this, well, that means I'm going to be doing the adjacent and the hypotenuse. So that's cosine. So cosine of 60 degrees has to equal cx over c, which that's going to be equal to cx over 150. And that's again cosine of 60 degrees. And if you plug in cosine of 60 degrees in your calculator with degrees, don't be in radians. I know that will be kind of an issue over the year because some people will be in different classes and have to be in radians and degrees. And I'll try to remind you as much as possible, like, are you in degrees? Are you in degrees? Are you in degrees? But we can write that and figure that out. Now, by the way, sometimes you'll notice, if I rearrange this algebraically, instead of writing it like this, sometimes, a lot of the times, actually, before I even plug in numbers, I will convert this formula, rearrange it algebraically, and I'll say, well, cx, the x component of c, is equal to the hypotenuse c times cosine 60 degrees. It makes it just, instead of the actual definition of cosine, it makes it more of a linear, it's not linear, but it's a one-line equation rather than having a fraction. And then again, you can plug in the value, and you can get the number. So if you do this, I plug in. If I can hit the right buttons, it'd be awesome. And I get a number, 75. I actually should have known that because of 60 degrees. So this is worth 75. And that would be newtons, by the way, because this is newtons, that's newtons. Now, I'm not writing units in because I'm just doing the kind of the math portion, but got to keep that in mind. So that's the x component. And then if I do the same thing for cy, well, that is going to be opposite of the 60 degrees over hypotenuse. That's sine is cy over c. You have to be careful because if you were to use this angle, sine isn't going to get you this. Sine would get you this if you use this 30-degree angle. So you have to be careful of the definition of sine and cosine and tangent with whatever triangle, whatever angle you're using. And if you have problems with trig, if you don't really know it that well, then you better make a separate little appointment with me to get that, to understand how to use sine, cosine, and tangent. Again, I will typically write this kind of in the one line one line kind of method. And we can plug it in. So that's 150 times the sine of 60 degrees equals. And if we do this, $129.9, I'm just gonna go to 130 here. I know I probably should keep that, a little more precise, but I'm gonna go to 130 newtons. Okay, and that would be cy, and that's gonna be equal to 130. And that's gonna be important. So that helps me